Welcome everyone. I am Dr. Rajesh Singh and this is part 2 of the video solution to exercise 4.2 Bartle and Sherbert. So in part 1 of the video I solved question number 1 to question number 5. In this video I will solve from question number 6 to question number 10. So let us start with question number 6. So as you can see in question number 6 we have to use definition of limit to prove the first assertion in theorem 4.2.4, that is we have to show this using epsilon delta definition. So what we have to show, let us start. So to show limit x tends to c f plus gx is equal to L plus M, and we are given that limit x tends to c f is equal to L and limit x tends to c g is also equal to M. So let us start writing the proof. So for epsilon delta definition we have to show that for arbitrary epsilon there should exist some delta such that mod f plus g minus L plus M should be less than epsilon whenever x belongs to the interval c minus delta to c plus delta. So for that we have to take any arbitrary epsilon. So let epsilon greater than 0 be any real number. So we have chosen any arbitrary epsilon. We have to show existence of some delta greater than 0 such that 0 less than x minus c less than delta should imply f plus gx minus L plus M less than epsilon. So this is what we have to show. This is our star. So first we will try to start with this and let's see what we get. So consider, so we'll start with this. So f plus gx minus L plus M. So this we have to show less than delta. So we will start with this. Now this is pointwise addition. So this is fx plus gx minus L minus M, and this I can write it as, this is fx minus L using triangle inequality. This is less than equal to fx minus L plus gx minus M. So now I want this to be less than some epsilon and this to be less than epsilon, so that this becomes epsilon. So I want this to be total, this to be less than epsilon. So what I will do, I will show that this is less than epsilon by 2 and this is less than epsilon by 2. So for this you make it as double star. Now as limit x tends to c fx is equal to L, so for epsilon by 2 greater than 0 there exists delta greater than 0 such that 0 less than x minus c less than delta implies fx minus L is less than epsilon by 2. So make it delta 1 because we will have another delta using g also, limit of g, so make it delta 1. Now again as limit x tends to c gx is equal to M, so for epsilon by 2 greater than 0 there exists delta 2 greater than 0 such that 0 is less than x minus c less than delta 2 implies gx minus M is less than epsilon by 2. So make it, mark it as, let me mark it as, so let me mark it as star. Okay, A, this is A, and this is B. Now A is holding for delta 1 and B is holding for delta 2. Now I want some delta such that A and B together hold for that delta, and we know what delta we should choose. We should take delta equal to minimum of delta 1 and delta 2. So for this choice of delta, A and B will simultaneously hold. So then, as 0 less than x minus c less than delta implies 0 is less than x minus c less than delta 1, and 0 is less than x minus c less than delta. So from A and B, it follows that 0 less than x minus c less than delta implies fx minus L is less than epsilon by 2, and gx minus m is less than epsilon by 2. So these two, A and B, is simultaneously holding for delta, for this delta, because we have chosen delta to be equal to minimum of delta 1 and delta 2. So for this choice of delta, A and B will simultaneously hold. So mark it as 3. So 3 triple star. Then I will use this triple star in my star. So this in my double star. So in double star, this is my double star. So in this, I will use triple star, because this will be less than epsilon by 2 and this will be less than epsilon by 2. So I will get this less than epsilon by 2. So using triple star in double star, we get 0 less than x minus c less than delta implies f plus gx minus L plus m is less than epsilon. Hence, by definition, by epsilon delta definition of limit x tends to c f plus gx minus L is equal to L plus m. So this we have shown using epsilon delta definition. So next, I am leaving this minus part because it is similar to plus. You just have to remove, replace plus by minus with little care, precaution, and then you will be able to obtain the proof of this. So I am leaving this part. I am going to solve this. Limit x tends to c, fg is equal to L plus m. So this I am going to prove now. So let's start with the proof of limit x tends to c, fg is equal to L plus m. So to show limit x tends to c, fg is equal to Lm, and we are given that limit x tends to c, f is equal to L, and limit x tends to c, g is equal to m. So let us start. So let epsilon greater than 0 be any real number. So we have to show there exists some delta greater than 0 such that 0 less than x minus c less than delta should imply fgx minus lm less than epsilon. So this is what we have to show. So let us start with this and see what it turns out. So consider fg of x minus lm. So fg of x minus lm can be written as fx, because this is pointwise multiplication, so this is fx into gx minus ln. Now what we will do, we will add and subtract fx m. So you can also add and subtract lgx and you will get the same results. This is similar to the proof which for the sequences, where we show that limit n tends to infinity, an bn is equal to ab. So it is similar to the proof of this result which we do in sequences. So what we have done, we have added and subtracted fxm. In this you can also add and subtract lgx. So now we will take common and we will do some manipulation. So this can be written as, I am taking fx common, so that will turn out to be gx minus m, and then from the second part I am taking m common, so plus m, so it will be fx minus l. You can see, so if I will take fx common from this, so I am taking fx common from this part and I am taking m common from these two. So when I will take fx common, so I will get gx minus x. When I will take m common, I will get fx minus l. So this is what we have. Now I will use triangle inequality. So using triangle inequality, I will get this fx into gx minus m plus m times fx minus l. So this I can write it as, using properties of moduli, I will get this plus mod m, because I don't know whether m is positive or negative, so I will take it in mod, and this. So now what I want to show, I using definition of limit, I can make this to be less than some epsilon, I can make this to be less than some epsilon. So I have to remove this by some constant. So for that I will use the boundedness of a function whose limit exists at a given point. So because limit of f at c exists, so f is bounded in some neighborhood of c. So we will use this fact to make it less than some constant. This is already constant, so I will not touch this. Now I will make it less than some epsilon by 2m and this epsilon by 2. So let us first use the boundedness criteria. So mark this equation as, mark this as star. Now as limit x tends to c, f exists, so f is bounded on some neighborhood of c, that is there exists delta 1 greater than 0 such that there exists delta 1 greater than 0 and k greater than 0 such that fx is less than equal to k for all x belonging to c minus delta 1 to c plus delta 1. This should be open to. So fx is less than equal to k for every x in c minus delta 1 to c plus delta 1. Mark it as a. So this is our a. Now what we will do again, as now because I want this to be less than, because this is less than k, so I want this to be less than epsilon by 2k. Then I will get total epsilon by 2 and I will take this to be epsilon by mod m, so I will cancel out these two things and I will get epsilon by 2 plus epsilon by 2, which will be equal to epsilon. So this is what I am going to do. So again, as limit x tends to c, gx is equal to m, so there exists delta 2 greater than 0 such that 0 less than x minus c less than delta 2 implies gx minus m is less than epsilon by 2k. So because k is positive, so this is positive. So for this epsilon, I am getting this delta 2 such that 0 less than x minus c less than delta 2 implies gx minus m is less than epsilon by 2k. So this I will mark it as B now. So now as limit x tends to c, fx is equal to L. So there exists delta 3 greater than 0 such that 0 less than x minus c less than delta 3 implies fx minus L is less than, now you can see here I want it to be less than epsilon by mod m mod 2m, so that this cancels out, but m may be 0 also. So if m is 0, then I may not be able to divide by epsilon by 2m, because if I will take epsilon by 2m and if my m is 0, then this will create problem because I cannot, this will become undefined. So what I will do, I will add plus 1 so that the case 0 is taken care of. So whenever such situation arises where you don't know whether a given number is 0 or not, so you can, what you can do, you can always add plus 1 to it. So you can add any positive real number. So I am adding plus 1 here because 1 looks good. So this is my C. So this is C now. So I want my A, B and C to hold for same delta. So what delta we should choose? We should take delta equal to, so we should take delta equal to minimum of delta 1, delta 2 and delta 3. Then from A, B and C we get 0 less than x minus c less than delta implies mod fx is less than equal to k. Second, gx minus m is less than equal to epsilon by 2k. And third, fx minus l is less than, this is strict, this is strict. So fx minus l is less than epsilon by 2 mod m plus 1. Okay. So now this I will mark it as double star. So I will use it in star. This is our star. I will use this, that double star in this star. So using double star in star, we get fgx minus lm is less than k times epsilon by 2k. We get for 0 less than x minus c less than delta. So for this x, this is true. So plus mod m into epsilon by 2 mod m plus 1. So here k gets cancelled out. I get epsilon by 2. Now mod m upon mod m plus 1 is less than epsilon 1. Is less than 1. So what I will do? I will replace mod m upon mod m plus 1 by 1. So we get, I will replace this mod m upon mod m plus 1 by 1. So I will get this is less than epsilon by 2 plus epsilon by 2, since mod m upon 1 plus mod m is less than 1. So I am replacing this term by 1, so I am getting the strict inequality here, and this is equal to epsilon. Hence we have shown for 0 less than x minus c less than delta fgx minus lm is less than epsilon. So by definition of limit x tends to c, fgx is equal to L. So this completes the proof of this. So let us go to the next question, which is question number 7, and let's see what's there in that. So in question number 7, we have to use the sequential formulation of the limit to prove theorem 4.2.4 B part. So we have to prove this using sequential criteria. So this is h is given to h does not vanish anywhere on a, and limit x tends to c, h is equal to h. We have to show limit x tends to c, f by h is equal to L by h. So let us start its solution. So solution given is limit x tends to c, h is equal to h. Limit x tends to c, f is equal to L, and hx is not equal to 0 for all x belonging to a. So hx does not vanish on a. To show limit x tends to c, f by h is equal to L by h, and this we have to do using sequential criteria for limits. So what we will do, we will take any arbitrary sequence xn in A such that xn converges to C, and we will show that f by h of xn converges to L by h, and that will prove this result. So let xn be any arbitrary sequence in A with xn not equal to c for all n belonging to n, and xn converging to c. So I have taken any arbitrary sequence xn in A such that xn converges to c. So I claim is f by h of xn, this sequence converges to L by h. So this is our claim. So now since limit x tends to c, f is equal to L, and limit x tends to c, h is equal to h, so by sequential criteria for limits, as xn converges to c, the corresponding sequences fxn converges to L, and hxn converges to h. Also, since h does not vanish on A, so h of xn is not equal to 0 for all n belonging to n. So we have two sequences, fxn converging to L, hxn converging to h, and hxn is not equal to 0 for all n belonging to n. So then by using the result, this if an converges to L, bn converges to h, and bn is not equal to 0 for all n, then an by bn converges to L by h. So I will be going to use this result. So using this result, what I get, fxn fxn by hxn converges to L by h, right? Now what next? So fxn by hxn is nothing but f by h of xn, that is f by h of xn converges to L by h. Hence by sequential criteria for limits, limit x tends to c, f by h of x is equal to L by capital H. So this completes question number 7. Now let us move to question number 8. So in question number 8, I have to first prove the inequality that minus x square is less than equal to xn is less than equal to x square for all x belonging to -1 to 1, and then I have to use this inequality to prove, and the fact that limit x tends to 0 x square is equal to 0, to show limit x tends to 0 x to the power n is equal to 0. So let us start. So solution, let x belonging to -1 to 1 be any element. So I am taking any element in -1 to 1. Then mod x is less than equal to 1. So this implies x to the power n minus 2. This is the trick. X to the power n minus 2 is less than equal to 1 for all n greater than equal to 3. So for any n greater than equal to 3, this is true. Why? Because mod x is less than 1. So if I will take any power of mod x, then that number is still less than equal to 1. So this is less than equal to 1. Now I can write this as this. So this implies I can take this power inside using modulus property. So this is less than equal to 1 for all n greater than equal to 3. Now I can use the modulus property, and this will be like this: xn minus 2 less than equal to 1 for all n greater than equal to 3. Now what I can do, since if I will multiply this inequality by a positive number, the inequality will be preserved. So I will multiply this by x square. X square is positive. So multiplying all sides by x square, I get this for all n greater than equal to 3, since x square is greater than equal to 0. And multiplying by a non-negative terms preserves the inequality. So inequality is not changed. I multiplied by x square and I have got the required inequality. So this is the required inequality. So now let us go to prove that limit x tends to 0 x to the power n is equal to 0. Since minus x square is less than equal to xn is less than equal to x square for all n greater than equal to 3, and limit x tends to 0 x square is equal to 0. So using squeeze theorem, we get limit x tends to 0 x to the power n is equal to 0 for all n greater than equal to 3. Hence the result. Now we need to let us move to question number 9. So what is the question number 9? We have been given that f and g are two functions defined on A, and C is some cluster point of A, and it is given that limit x tends to C, f exists, and limit x tends to C, f plus g exists. Then we have to show that limit x tends to C, g exists. So solution, A part, given is limit x tends to C, f exists, and limit x tends to C, f plus g exists. To show limit x tends to c, g exists. So what, since limit x tends to c f exists and limit x tends to c f plus g exists, so let limit x tends to c f is equal to L and limit x tends to c f plus g equal to m. Claim, we will show that limit x tends to c, g is equal to m minus L. So this is what we are going to show. So let epsilon greater than 0 be any real number. So I am taking any arbitrary epsilon. Now consider gx minus m minus L. So now what we will do, we will add and subtract fx here. So gx plus fx minus m plus L. So I have added and subtracted fx in this. Now I will combine this. So this will become fx plus gx minus m minus fx plus m. So I have just rearranged these terms. Now I can write this as f plus gx minus m minus fx minus L. Now using triangle inequality, what I will get? This will become fx minus, so this will be plus, so fx minus L. So using triangle inequality, I have got this. So now using the limit, I will be able to show that this is less than epsilon by 2 and this is less than epsilon by 2. So first let us mark, so let us first mark this as star. So using, now I will use this. So now as limit x tends to c, fx is equal to L and limit x tends to c, f plus gx is equal to m. So there exists delta 1 greater than 0 and delta 2 greater than 0 such that 0 less than x minus c less than delta 1 implies fx minus L is less than epsilon by 2 and 0 less than x minus c less than delta 2 implies f plus gx minus m is less than epsilon by 2. So make this A and make this B. So I want A and B to hold simultaneously for same delta. So what I will do, I will choose delta, let delta equal to minimum of delta 1 and delta 2. Then from A and B, it is clear that 0 less than x minus c less than delta should imply fx minus L is less than epsilon by 2 and f plus gx minus m is less than epsilon by 2. So this is double star. So now I will use this double star in my star to get my desired result. So using double star in star, we get 0 less than x minus c less than delta implies gx minus m minus L is less than epsilon by 2 plus epsilon by 2, which is equal to epsilon. So by definition of limit x tends to c, by definition of limit x tends to c, gx is equal to m minus L, and that is limit x tends to c, g exists, hence the result. So we have proved the first part. Now let us prove the second part. What is second part? Second part is that we have to if limit x tends to cf and limit x tends to cfg exists, does it follow that limit x tends to cg exists? No, it does not follow. So let me give you an example. So let me consider this example. Let fx equal to 0 for every x in R. Clearly limit x tends to c, x tends to 0 f exists, and gx is equal to signal function of x for all x belonging to R, which is equal to -1 if x is less than 0, 0 if x is equal to 0, and 1 if x is greater than 0. Then we know that limit x tends to 0 f exists, and fg is our function. Fg of x is equal to 0 for every x in R. So clearly limit x tends to 0 f exists, and limit x tends to 0 fg exists, but limit x tends to 0 g does not exist. So this is one simple example to show that limit f may exist and limit fg may exist without limit g being existing. So we are done with question number 9. Let us move to question number 10. So in question number 10, we have to give examples of functions f and g such that both f and g do not have limits at point C, but both f plus g and fg have limits at C. So we have to give examples of this function. So let me give you one simple example. Solution: you can take fx equal to 1 if x belongs to Q and 0 if x does not belongs to Q, if x belongs to Q complement, and gx equal to 0 if x belongs to Q and 1 if x belongs to Q complement. Then we know that Dirichlet function do not have, this function does not have, the limit for this function does not exist anywhere. So Dirichlet function, I am taking the example of Dirichlet function. So you can take any point. So for any C belonging to R, limit x tends to C f and limit x tends to C g does not exist. Now what is f plus g? In both the cases it is easy to see that f plus g is a constant function 1 and fg is a constant function 0. So it is easy to see that all f plus gx is equal to 1 for every x in R, and fgx is 0 for every x in R. So clearly limit x tends to C, f plus g exists and equals 1 for all C belonging to R. So you can take any point C and you will see that the limit exists, and limit x tends to C, fg exists and equals 0 for every C in R. So this is the example of functions f and g such that f and g do not have limits at a point C, but f plus g and fg both have limits at C. So these are some simple examples that you must remember, and you can always construct such examples using these Dirichlet functions or signum function. So this is all I have in this video. Thank you for watching. Please do subscribe the YouTube channel for further updates and for more such videos. Thank you.